Welcome to this crash course on programming the mBot2 in Python. In this course, we will learn the following 5 topics. First, we'll program the ultrasonic sensor in a simple Python project to get started. We'll then learn about proportional control line following and the logic behind this algorithm. Then, we'll implement it in a Python program. Next, we'll add color sensing and obstacle avoidance to our proportional control line follower. Finally, we'll write a Python program from scratch in which the robot makes different sounds when tilted in different directions. This is a compilation of 5 previous projects all in one video, and after just 1 hour of following along with this video, you'll have enough knowledge and practice to explore and build your own robotics projects in Python with the mBot2. So without further ado, let's get started. As long as you have some Python programming experience, you should be able to follow along this programming exercise. For example, if you know what import statements, variables, and functions in Python are, you should be good to go. If you don't have any experience with Python, you can learn from several resources here on YouTube. Just search for Python basics and there will be several videos from other YouTubers that cover these basic concepts. Once you have that covered, come back here to continue. Let's first take a look at our block program that we built in our ultrasonic sensor intro video. This is a simple program that says that when button B is pressed, we will get the ultrasonic sensor distance, print it on the CyberPi display, and move to a new line. Let's convert this block program to Python code. To do this conversion, we will need some reference documentation. Unlike in block programming, where we have the block categories on the left pane, when we get into Python land, we would not have something similar within the editor that shows all the functions that we can use. Instead, we will need to refer to some online documentation, specifically the API docs by yuque.com. So what does API docs mean? It stands for Application Programming Interface Document. This is the document that lists all the functions that we can use in our program. This is similar to the block categories that we used in block programming, but instead of blocks, it lists all the Python functions that we can use. There are 2 web pages with relevant documentation. First is the CyberPi API docs page. This page contains APIs that help our program control elements of the CyberPi module. This can be things like events, display, audio, and many more. As an example, if you need the functionality of the when button A pressed block from the events block category, but want to implement that in Python, you should look into this document. The second document is the mBuild Python API docs page. Here, you will find APIs for sensors like the quad RGB sensor, ultrasonic sensor, ambient light sensor, and more. This document has more than just sensor APIs, but let's start there for now. We will explore more as needed by our future projects. I'll add links to both of these documents in the description. I highly recommend bookmarking them in your browser so that you can access them easily. We will be going back to these docs in almost every Python programming tutorial going forward. Let's now look at the APIs that are needed for this project. To do that, let's look at our block program and think of the block categories that we used when we were building them. The when button B pressed block was from the events block category. The print and move to a new line block was from the CyberPi display category. And finally, the ultrasonic distance to object block was from the ultrasonic sensor 2 category. As you would expect, the button B and print blocks relate to elements on the CyberPi. So we should look into the CyberPi Python API docs to find the APIs for these. For the ultrasonic sensor 2 API, since most sensor APIs outside of the CyberPi are in the mBuild Python API docs, we should look there to find the API for the ultrasonic distance measurements. Now let's head over to the documentation pages and find the APIs that we need. We are now in the CyberPy Python API document. From this document, we identified that we needed to find two APIs. First is the when button be pressed event block. Make sure that you have the outline enabled on the right-hand side pane. If you don't see this, you may need to toggle the right side pane by clicking on this button. To find an event API, let's scroll down the outline and see if we can find events anywhere. Yes, we see events here, so let's click on that. Here, we see examples of how to use events. Events are designed to be decorators in Python. If you aren't familiar with decorators in Python, let's take this first piece of code as an example. The goal of this code is to turn the LEDs green as soon as the CyberPy starts up. Here, the event is the CyberPy starting up, and the action is to turn on the green LEDs. You can see the function called callback that defines the action, turn on the green LEDs. We want to call this function automatically when the CyberPy starts up, which is the event. The way to do this is by using the cyberpy.event.start decorator. To add a decorator, you go one line just above the function definition, and you start with an @ symbol followed by the name of the decorator. In our case, we want to do something when button B is pressed. We don't want to do it when the CyberPy starts. So we will have to find a different decorator that does what we want. Let's scroll through the list here to see if we can find one. Let's skip the first one because that is when the CyberPy starts. Looking at the second one, this seems promising because it's saying when something is pressed. Now we want button B pressed, so we've got to see if that is supported by this API. How can we find that? Let's look at what we can pass into this function. Name is a string, and it is the name of one of the buttons or the joystick direction. So we're getting closer here, so we're looking for button B, and we see that button B is supported by this function, and this would be perfect for our use case. So we will use this decorator to detect the event when button B is pressed. Next, we need to find the API similar to the print and move to new line block. Since this is a display functionality, we can expect to find it under display in the outline. Let's click on display. We see two APIs that say print. So what's the difference between them? Print by default does not automatically force a new line, whereas println forces a line break, as is mentioned in the documentation here. Line break is just another way of saying a new line. So this API is what we will use for our project. Great, so now we have 2 out of the 3 APIs needed for our project. Next, let's go to the mBuild Python API docs and look for the last API that we need. Now we're in the mBuild API page. We're looking for the ultrasonic sensor distance measurement API. Scrolling through the outline once again, we see the ultrasonic sensor 2 section. Let's click on that. The very first API that we see here gives us the ultrasonic distance between an obstacle and the ultrasonic sensor. This is perfect for our project, so we'll use this API. Now let's update this page with the APIs that we chose. Awesome! Now we're ready to start programming. Before we jump into programming, I want to mention that I was having trouble with the Python programming using the web editor. So from this video onward, I'll be using the mblock desktop application. To download this desktop application from the mblock website, click on Download. Scroll down and select the version that is suitable for your computer. I'm running Windows, so I downloaded this version. Then follow the installation steps once the download has completed. This is the desktop app, and it looks very similar to the web version we were using in the previous videos, so this should feel very familiar to you. Let's first give our project a name. I'm going to call it Tutorial 11 Ultrasonic Python. And once we have that, we click outside and we've renamed our file. Now let's add the mBot2 device by clicking Add, selecting the mBot2 robot and clicking on OK. Next, we'll switch to the Python mode by clicking on Python over here. We have our block program on the right side for reference. I'm going to first add a few comments to describe what I want the program to do briefly. First, we need to import any modules that are required. And then we're going to use the button be pressed decorator. So I'll say use decorator for button be press event. And finally, after that, we're going to define a function that prints the ultrasonic sensor distance measurements and moves to a new line. Now that we have these comments, you can clearly see the structure of the code and what needs to be done. For the imports, we need both the CyberPy and the mBuild modules. So we'll import CyberPy, mBuild. The decorator that we chose to use from the API docs was the cyberpy.event.isPress decorator. So let's add that. We start off with the @ symbol. So we say cyberpy.event.isPress, and the parameter that we want to pass is b, so that we get button B. Now let's define the function. I want to call the function on button B press because this function will define what we do when the button B is pressed. Within our function, we want to print the distance and move to a new line. So we'll use the cyberpy.console.println API. And the parameter that we want to pass here is the ultrasonic distance measurement. To get the ultrasonic distance measurement, we'll use the mbuild.ultrasonic2.get, and optionally you can pass the ultrasonic ID, which is 1. If you have more than one ultrasonic sensor, this might be different, but if you have just one, like the standard mBot2 robot, you can leave this as 1. And that's it. Now let's upload the code and test it on the robot. To upload, first make sure that you have the robot powered on and connected to your computer. Then let's switch to the upload mode, click connect, and select the COM port for your robot. Select connect. Now that we've connected, we can go ahead and click upload code. Wait for the upload to complete, and voila, we're done now. Now that we've uploaded the code, let's go ahead and test it out on the robot. Let's first place an obstacle far away from the robot and press button B. We see that the distance reported is 44.9 centimeters. Now let's bring the obstacle closer. We now see that the distance reported is 8.6 centimeters. Finally, let's place the obstacle in between the two distances, and we should see a distance reading which is in between the two as well. We see a distance reading of 27.8 centimeters. Great, our program works as expected. Let's first look at what proportional control actually means. If you've already watched this section in one of my previous videos, feel free to skip to the next lesson. The timestamps are in the description. For an analogy, think of driving a car. If you drift slightly off the road, you gently turn the wheel. But if you are way off, you turn the wheel more sharply to correct your path. That's exactly how proportional control works. It adjusts the correction based on how far off you are. So what do we need to implement proportional control? First, we need an error signal. In our case, this is called deviation, a number that tells us how far off the robot is from the center of the line. The quad RGB sensor provides this automatically in mBlock using the deviation block. Second, we need a stronger correction for larger deviation and a weaker correction for smaller deviation. If the robot is slightly off, it corrects it gently. If it's far off, it makes a stronger turn. And to achieve this correction proportional to the amount of deviation, we will need a couple of equations that dictate how much power is to be sent to each of the left and right motors. The error signal is given to us directly by the mBlock using the quad RGB sensor's deviation block. However, the equations is something that we need to explore. Now let's break down the equation for proportional control. Our goal is to adjust the motor speeds based on how far the robot is from the center of the line. Let's first define three variables. First is base power. This is the default speed when the robot is centered and driving straight. Second is Kp. This is called the proportional gain, which is a correction factor. Larger values of Kp mean stronger corrections. Third is deviation. This is provided by the quad RGB sensor and ranges from -100 to +100 and is a measure of how far off the robot is from the center of the line. Now let's look into what the values reported by deviation means. A large positive value for deviation close to +100 means that the line is far left of the robot. A small positive value, close to 0 but still positive, means that the line is slightly left of the robot. A deviation value of 0 means that the line is centered. A small negative value, close to 0 but still negative, means that the line is slightly to the right of the robot. And finally, a large negative value, close to -100, means that the line is far right of the robot. Now that you know what the deviation values mean, let's look at the equations. These are the equations. Computing the left and right motor's power is done by taking the base power and adjusting it by a factor that is proportional to the deviation from the center of the line. To understand these equations better, let's walk through 5 examples. Let's keep our formula on top for reference. We will then make a couple of assumptions. We will assume that the base power is at 30% and Kp, which is our proportional gain, is set to 0.3. You can play around with these numbers if you want. Increasing the base power will increase the overall speed of the robot. Increasing Kp will increase the strength of the corrections, so the robot will more aggressively correct for higher values of Kp. So let's look at the first example where the deviation value is +100. The left and right power calculations are as follows, and they result in the values of left power being 0 and right power being 60. As you can imagine, this means that the robot is going to make a sharp left turn. And this makes sense because with a deviation value of +100, it means that the line is to the left of the robot, and in order to perform a correction, the robot needs to turn sharp left to get back on track. For the second example, we will assume a small positive deviation value of +30. The left and right power calculations look as follows, and they result in values of 21 and 39. As you can see, they are not very far off from the base power of 30. The left power is slightly lower and the right power is slightly higher, indicating a gentle left turn. This also makes sense because with a small positive deviation value, it means that the robot is slightly left of the line and a gentle left turn would be sufficient to bring the robot back in alignment. For the third example, we will take a 0 deviation value, which means the line is perfectly centered. The left power and right power calculations are as shown here, and they result in the left power and right power both being 30. So with equal power sent to both wheels, this means that the robot drives straight, as expected when the line is centered. Next, we'll look at a small negative deviation case. We will assume a small negative deviation value of -30. The left and right power calculations are shown, and they result in the left power being 39 and the right power being 21. As you can see, this corresponds to a gentle right turn, which makes sense because with a small negative value for deviation, the line is slightly right of the robot, and performing a gentle right turn will bring the robot back in alignment. Finally, let's take the case of a large negative value of -100. The left and right power calculations are shown, and they result in the left power being 60 and the right power being 0. This indicates a sharp right turn, which makes sense because the line is far right of the robot and we need to correct stronger in order to get back on track. Finally, there's one small modification that needs to be done to the equations. This is to account for the fact that the right motor actually drives backward when given a positive power and drives forward when given a negative power. This is opposite to the left motor's direction and is because of the way that the motors are mounted opposite to each other on the chassis. In order to account for this, we will multiply the right motor power by a -1, and that inverts the direction. Alright, great job so far. We have our final equations. Now that you understand how proportional control works, let's build the program in mBlock. To write a Python program for proportional control line follower, we'll use this block program as a reference guide. As we established in the previous section, this block program has the final equations for the left power and right power, but we'll now walk through this program step by step so we understand what's going on here before converting it to a Python program. This program says that when button B is pressed, we initialize our variables and then loop until button A is pressed. Pressing button A will stop both the wheels and exit the program. Within the loop, we get the deviation value reported by the quad RGB sensor and then calculate the left and right power based on this deviation value. We then command these power values to the wheel motors of the robot. Let's convert this block program to Python code. To do this conversion, we will need to refer to the API docs like we did in our previous video. I introduced these two API docs in the previous video. In this tutorial, in addition to these two, we're going to refer to a third API doc as well. This is the mBot2 Shield Python API docs page. This page contains APIs that relate to motion commands like drive forward, turn, etc. I'll add links to these web pages in the description. I highly recommend bookmarking these in your browser so that you can access them easily since we will be using them often. Let's now look at the APIs that are needed for this project. To do that, let's look at our block program and think of the block categories we used when building it. The when button B pressed was from the events block category. The was button A pressed was from the CyberPi sensing category. The quad RGB sensor deviation block was from the quad RGB sensor category, and finally the encoder motor left and right power blocks as well as the stop encoder motor blocks were both from the mBot2 chassis category. Now you might have noticed that we have not covered all of the blocks here. For example, we have these variable blocks, this repeat until control block, and the green operator blocks. The reason that we're not going to look for APIs for these is because Python by itself allows us to do things like set variables, loop until a condition is met, and perform basic arithmetic operations. So we don't need a specially built API to achieve those functions. This means that we need to find APIs only for the blocks marked in red here. We then have to think about which page we would need to refer to in order to find these APIs. Since the button B press and button A press blocks are buttons on the CyberPi, we can start by looking into the CyberPi Python API docs. Since the quad RGB sensor is a sensor, we can first check the mbuild Python API docs. Since the motion command APIs are likely to be in the mBot2 Shield Python API docs, we will start by looking there for the motor power and stop motors blocks. Now let's head on over to the documentation pages and find the APIs that we need. We are now in the CyberPi Python API document. If you don't see this outline pane on the right side, you may have to toggle this button to open or close the outline pane. We identified that we need to find two APIs from this CyberPi API doc. First is the when button B pressed event block. In our last video, we used the isPress event decorator that we can find under events by scrolling in the outline pane. So if you go to events and scroll down a bit, we see this isPress decorator, which is the one that we used for button B press. We'll use the same API this time as well. Next, we need to find the sensing API for button A pressed. Since we're going to be checking for button A press within the loop, we cannot use a decorator like we did for button B. Let's look for sensing because this is a sensing API. In the outline, we see sensing right here. Click on that, and the very first API here is cyberpy.controller.isPress, and the argument or the parameter that it takes also supports button A, which is exactly what we need. So we'll use this for checking if button A is pressed within the loop. Now we're in the mBuild API page. We're looking for the quad RGB sensor deviation API. Scrolling through the outline, we see under sensors that there's the quad RGB sensor section. Let's click on that. The very first API gives us the line status, which is not really what we're looking for. We want to get the deviation value. So keep scrolling and let's look at the next one. This API says get offset track, and let's read its description. It says obtains how much quad RGB sensor deviates from the line to be followed, and it returns an integer ranging from -100 to +100. So this API is the one that we need for our project here. Finally, for the APIs related to motion commands, we're now at the mBot2 Shield API page. Here, let's click on Motion under the mBot2 Shield section. First, we're looking for an API that takes two values, one for the left wheel power and the second for the right wheel power. So let's look for an API that supports providing power values to it. We see a forward API which doesn't look like what we need, then there's a backward which is also not what we need, turn left, turn right, straight, turn. And here, this is something that's interesting to us. So we see a drive power, and it does take in two power values for EM1 and EM2. EM1 is the left wheel, whereas EM2 is the right wheel by default. So this is the exact API that we want to use for our project. The last API that we're looking for is an API to stop both the wheel motors of the mBot2. Continuing to scroll down, we see the mBot2.emStop API. This stops the specified motor, and we have the option to stop all motors, which fits our requirement. Coming back to our presentation now, we can clean this up a little bit. Since we're only interested in identifying the APIs, let's clean up everything else. I'm going to now split the two mBot blocks into separate items here. Now let's record the APIs that we need to use for each of these blocks as we had identified from the API documentation pages. Awesome! Now that we have all the APIs identified here, we're ready to start programming. First, open your mBlock desktop application. Now let's give our project a name. I'm going to call it Tutorial 12 Python Proportional Line Follower. Add the mBot2 device by clicking on Add and then selecting mBot2 and click OK. Switch to Python mode by clicking on Python here. We have our block program on the right side for reference. Let's add some comments now to form the structure of our program. First, we need to import the required modules. Then, we're going to use the button B pressed decorator and define a function that replicates the steps in the block program. The steps in the block program are: first, we will initialize the base power and KP variables. We will then loop until button A is pressed, and within the loop, we will get the deviation from the quad RGB sensor. Once we have the deviation value, we will calculate the left power and right power values. Then, we will command the left and right power to the motors. Finally, outside the loop, we will stop the motors before quitting the program. Now that we have these comments, you can clearly see the structure of the code and what needs to be done. For the imports, we need to import the CyberPy module, the mBuild module, as well as the mBot2 module. The decorator that we chose to use from the API docs was at cyberpy.event.isPress, and the button we're looking for is button B. Now we can define the function. Let's call our function onButtonBPress. Within our function, we want to first initialize base power to the value of 30 and kp to the value of 0.3. Then we'll start the loop. We need to loop until button A is pressed. We can use a while loop here. We need to be careful about setting the condition for the while loop. We want to keep looping as long as button A is not pressed. So the condition should be while not cyberpy.controller.isPress, and the button we're looking for is A. Within the loop, we'll first get the deviation value. So let's initialize a new variable called deviation and set it to the value returned by the API mBuild.quadRGBSensor.getOffsetTrack, and the index is 1 because we have only one quad RGB sensor. Now we can calculate left power as base power minus kp times deviation. This is from our equations for proportional control. We can then calculate right power as -1 times base power plus kp times deviation. Now let's command the power values to the motors. We will use the mBot2 API, mBot2.drivePower, and pass in the left power as the first argument and the right power as the second argument. Finally, outside the loop, we'll command a stop to both the motors. We'll do this using the mBot2.em_stop and pass all to stop all motors. And that's it! We're now done with the proportional control line follower project in Python. So let's save the code for this project. We can now upload and test it out on the robot. To upload, make sure you have the robot powered on and connected to your computer. Then switch the mode to upload and click connect. Select the COM port for your robot and select connect. Once it's connected, you can go ahead and click upload code and wait for the code to be uploaded to the mBot2. Now that we have the code uploaded, let's test it out on the robot. Let's test our proportional control program using the makeblock line follower sheet. Press button B to start the program. The robot follows the line pretty closely, making fine adjustments as needed to stay on track. Press button A to stop the program. Let's continue from where we left off in the proportional control program. We will add some comments to mark where we want to insert the new logic. Before we edit anything in this program, let's make sure to save this as a new file. So select File, Save As, and give your project a new name. I'm going to call this Tutorial 13 Python Color Obstacle Avoidance and Advanced Line Following, and say OK. Once it's saved, make sure that you're in your new program before you edit the code. First, we want to do color sensing. We want the robot to detect green, and if the robot detects green on the L1 or R1 sensors, we want the robot to do a 180-degree turn. I'm going to move the reaction to the next line here just to make it clearer in the comments. Next is obstacle detection. If the ultrasonic sensor detects an obstacle less than 10 centimeters away, then we want the robot to stop and wait for the obstacle to be removed. If neither of these conditions are true, continue advanced line following. Now that we have the structure of our code, let's go to the mBuild API section of the Python documentation to get the APIs for color sensing as well as obstacle detection. Later, we will go to the mBot2 section of the Python documentation to get the robot commands for a 180-degree turn and to stop and wait. Let's head over to the documentation pages now. We are now at the mBuild API page. First, we want to find the API for color sensing. So let's scroll down to the sensors part of the outline and look for the quad RGB sensor. Let's look at the different APIs that are available. So we have get line status, we have get offset, is line, is background, is color. So this is interesting because we want to detect color, specifically the green color on L1 or R1. So let's see if this API can provide us what we need. The first argument that we can provide to this API is the color, which is great because we want to detect green. The second argument is CH, which doesn't make much sense, but let's look at the documentation to see what we can provide there. CH says that we can provide any of these strings, L1, L2, R1, R2, or lowercase l1, l2, r1, r2, or the integers 1, 2, 3, and 4. For us, this is perfect because we are interested in getting the green status of L1 and R1 sensors. So this would be the API that we use for color sensing. Let's now move on to the API for obstacle detection. Since for obstacle detection we're going to use the ultrasonic sensor, let's scroll down to the ultrasonic sensor 2 category. And in here, we see the very first API, and we've also used this previously. It is the ultrasonic sensor 2.get API, which gives us the distance between an obstacle and the ultrasonic sensor. This is perfect for our use case here, so we will take this API for detecting obstacles. Let's now head over to the mBot2 shield page to find the documentation for turning as well as stopping all motors. We're now in the mBot2 shield documentation page. So let's go over to motion. The first thing we're trying to find is the turn 180 degrees command. Looking at these APIs, forward is not something that we're trying to do right now, neither is backward. Turn left is interesting. Let's look at this. We want to turn 180 degrees, so we want to be able to provide a turn angle. However, this API takes in a speed to turn at, as well as t. And if you look at the documentation, t is indicating the duration of the turn, not really the angle of the turn. So this API is not what we are looking for. The same issue is with the turn right API. It does not take in an angle. Straight is not what we're looking for. And finally turn. So this is interesting because it does take in an angle for the turn. It turns clockwise, but that is fine. We don't really care about the direction of the turn. We just want to turn 180 degrees. We can also specify a speed for the turn, which is an added benefit. This API is the one that we will use for making the robot turn when it detects green. Next, we need to find the API to make the robot stop when it detects an obstacle. That is something that we've done in the past. We've used the EM stop API and provided all as the argument to stop both the encoder motors. Once again, we will use the same API to make the robot stop when it detects an obstacle. Now that we've identified all the APIs, let's head on over to mBlock and continue writing our program. Now let's implement the logic. We want to first do color sensing, so we'll use the mbuild.quadrgbsensor.isColor API. The first argument is the color that we want to sense. The second argument is the channel that we want to sense at, which is first L1. And we can leave the third argument alone because that is the index and it defaults to 1. So now that we've added logic for checking if L1 detects green, we also want to check if R1 detects green, and we want to use the OR operator in between them. This is because if either L1 or R1 detects green, we want to react to it. In order to detect green on R1, we can simply copy this API call that we made here and paste it at the end and simply change L1 to R1. So now that we have our condition defined, the reaction we wanted to do was to turn 180 degrees. To turn 180 degrees, we found the API mBot2.turn, and this takes in the angle to make the turn and a speed. We'll leave the speed as is because it has a default of 50 RPM. Next, let's focus on obstacle detection. We want to perform obstacle detection only if green was not sensed by the color sensor. So we will do this using the elif statement in Python. We now want to get the ultrasonic sensor distance value, so we'll use the mBot2.ultrasonic2.get API and check that the distance is less than 10 centimeters. If it is less than 10 centimeters, we want to stop and wait in this case. In order to stop and wait, we'll use the same mBot2.emStop of all API call. So I'm going to copy and paste that over here. Finally, we want to continue advanced line following only when neither of the above conditions are true. That is, if no green was sensed and no obstacle was sensed, only in that case we want to continue advanced line following. To make this possible, we'll move the entire advanced line following into the else part of this conditional block. To indent an entire block of code to the right, select the block of code that you want to indent and then hit Tab once. Now the entire advanced line following logic is within the else block. Make sure to save your code, and that's it. You've now added color sensing as well as obstacle avoidance to our previous line follower code. Let's now upload and test this code on the mBot2 robot. To upload, first make sure to power on the robot and connect it to your computer using the USB cable. Make sure you're in the upload mode and click connect. Select the COM port for your robot, click connect again. Now that the robot's connected, let's go ahead and click upload code. Wait for the upload to complete, and it's done. Let's now take the robot and put it on our test track and see how it performs. For the testing setup, we're using the standard makeblock line follower sheet with the green square on its path. When the robot detects green, it performs a 180-degree turn, and when an obstacle is introduced within 10 centimeters, the robot stops and waits for the obstacle to be removed. Otherwise, it continues to follow the line. Let's start the robot by pressing button B. The robot begins following the line. On detecting the green square, it does the 180-degree turn and continues in the opposite direction. When we introduce an obstacle, it stops. Once the obstacle is removed, it resumes line following. Upon hitting the green square again, it performs another 180-degree turn. We can stop the program by pressing button A. Let's open mBlock and start a new Python project. Let's name the project. I'm going to call it tutorial 14 tilt sounds. Let's first add comments to define the structure of our program. I'm going to add a multi-line comment here. As always, we will start the program when button B is pressed, and we know that we can use the button B event API from our previous tutorials. When button B is pressed, the first thing we want to do is print on the display the words detecting tilt. We then want to repeat until button A is pressed the following instructions. First, we want to detect if the robot is tilted forward. So we will say if tilted forward. We want to play a specific audio track. So let me just say for now, play audio track 1. And similarly, if it is tilted backward, we want to play a different audio track. I'm just going to call it audio track 2 for now. And we're going to repeat the same for if tilted left as well as if tilted right. Finally, when button A is pressed and we're about to end the program, let's clear the CyberPy screen because we had previously printed detecting tilt when the program started. So we're going to clear the display after button A is pressed before ending the program. Now we are familiar with some of these APIs that we would use here because we've used them in our previous programs. For example, for the onButtonB event, we can use the API cyberpy.event.isPress, which is a decorator. For printing on the display, we can use cyberpy.console.println. To detect if button A is pressed, we can use the cyberpy.controller.isPress. The APIs that we need to figure out are for tilted forward, We've never tried this before, so this is new. Similarly, playing an audio track, tilted backward, tilted left, tilted right. We also don't know for play audio track 2, 3, and 4, but we are going to assume that there's just one API that lets us play different tracks. So as long as we find out what the API is for play audio track 1, we can change the audio track itself that we want to play, but use the same API. And finally, we also want to find out the API for clearing the display, because that's something that we haven't done in the past. So let's write down the list of APIs that we need to find so that it is clear. So we need tilted forward, tilted back, tilted left, tilted right, play audio track, and finally clear the CyberPi display. Let's head on over to the CyberPi Python API documentation page to find these APIs. As always, the links to the API docs are in the description. We are now in the CyberPi API page. The first 4 APIs that we need are related to tilt detection. Let's glance over the outline to check if we see tilt detection mentioned anywhere. It's not likely to be in the audio section, and the same goes for the display section. Sensing maybe, but looking at the subheadings, it's not really clear that tilt detection APIs could be in any of these. It may be in sensor outputs or other outputs, but it's hard to say. Let's continue looking. It could be in motion sensing. Posture seems like a place it could be in, but that isn't super clear either. Wi-Fi, cloud services, broadcast, and events all seem unlikely. So we couldn't directly find tilt detection from the outline. In cases like this, we have 2 options. One is we could start with a likely subheading like sensor outputs and keep scrolling until we find tilt detection APIs. Another option is to do a browser search. So in your browser, you can hit Ctrl F or Command F if you're on a Mac computer, then type in tilt, and we found the tilt detection APIs without any scrolling. Here we see there are APIs for tilt forward detection, tilt back detection, tilt left detection, and tilt right detection, which are the 4 APIs that we're looking for. And we will use all of these since we want to detect all 4 directions of tilt for our program. Next, we need the audio playback API. For this, we can use the outline. We see the audio section, so let's go there. We see 2 APIs here, play until and play. Both take in the name of the music to be played, which the documentation says is defined by the table in this link. This table is the same one that's right here, below the 2 API definitions. Before we start looking into which audio track we want to play for each tilt direction, let's figure out which of the 2 APIs we want to use, play until or play. Reading the documentation, it says that play until blocks the thread until the playing ends, whereas it does not say that for the play API. So what does blocks the thread mean? In simple language, it means that in our Python program, when we make a call to play until, which is the blocking API, the program will wait until the audio file is fully played back before executing any next instructions in the program. Whereas with the play API, it will start playing the audio track and continue executing next instructions while the audio continues playing. For our project, we want the audio to fully play and not get interrupted by any other audio track. So we will use the play until API. Now that we know that we want to use the play until API, let's go and figure out what sounds or what audio tracks we want to use for the different tilt directions. To do that, we can refer to this table, which is right down here. We have 4 tilt directions that we're going to detect, so we need 4 different audio tracks. Feel free to explore this table and choose any 4 out of all of these different audio tracks that you have available to you. I'm going to choose 4 different tracks here. So for tilt forward, I want to play start. For tilt back, I want to play laser. For tilt left, I want to play clockwork. And finally, for tilt right, I want to play jump. Finally, we need to find the API to clear the CyberPi display. Since it is not clear from the outline which subheading the clear API would be in, let's use our browser search function. Let's search for clear, and we have the cyberpy.display.clear API, which clears the CyberPy screen and is exactly what we want. Great! Now that we have all the APIs we need, let's get coding. First, before we get into programming the logic, we need to import any required modules. In our case, since all the APIs that we need are from the CyberPy module, we will simply import CyberPy. We can document the APIs by replacing all the question marks right here. Now that we have all the APIs, we can remove this section from our comments. Now let's implement the logic. The first thing we want to do is to start with the event decorator for button B press. So that is cyberpy.event.isPress, and the button we're looking for is button B. Let's name the function. I'm going to call it onButtonBPress. The first thing we want to do is to print on the display detecting tilt. So we'll use the cyberpy.console.println API, and the text we want to print is detecting tilt. Now we want to repeat until button A is pressed, so we'll use the while loop here. So we want to repeat while button A is not pressed. So we're going to do cyberpy.controller.isPress and button A. The actions we want to repeat are: first, check if the robot is tilted forward. If the robot is tilted forward, we want the CyberPy to play an audio track, for which we will use the play until API. And the audio track we want is start. I just realized that I missed updating the comments for which audio tracks we're going to play here, so let's do that now. First, we decided that for tilted forward, we want to play the start audio track. For tilted backward, we want to play the laser audio track. For tilted left, we will play the clockwork audio track. And for tilted right, we'll play the jump audio track. Now let's continue with our program. We want to do the same thing here, just that we want to detect different directions of tilt. So I'm going to copy and paste the tilt forward code and change the tilt forward to tilt back, and also change the audio track we want to play to laser. Similarly, we want to detect tilt left, and the audio track we want to play for left is clockwork. And finally, we want to detect tilt right, and the audio track we want to play there is jump. Finally, if button A is pressed and we exit this while loop, we want to make sure to clear the CyberPy display before quitting the program. Make sure to save your program, and that's it. I know you're excited to test this out on your robot, so let's first upload the program. Make sure that the robot is powered on and connected to your computer. Click Connect, select the COM port for your robot, select Connect again. Make sure you're in the upload mode, and finally click on Upload Code and wait for the upload to complete. Now for the exciting part, let's go test our program on our mBot2 robot. To test the program, let's first press button B. We see the detecting tilt message. Now let's tilt the robot forward. We hear the start audio track. Next, let's tilt it backward. That's the laser audio track. Let's tilt to the left. We hear the clockwork audio track. Finally, tilting to the right, we hear the jump audio track. Let's press button A to stop the program. Here are some of my other videos that you may find helpful. Happy programming, and I'll see you in the next one.